Hi, folks. I want to try something kind of interesting, something I haven't tried before. Um, and maybe it'll work, maybe it won't, but we'll see. As we head into our section on our trigonometric identities, we're going to learn or get exposed to a whole bunch of new tools and how to use those tools. The nice thing is all these new tools are really applications of the tools we already know. Really, our first chapter is about all these new measuring systems, all these new functions and how they work. This chapter is really how to manipulate them and seeing some of the things that they can do. For example, as we started, we learned things like that the secant function we can think of as the reciprocal of our sine function. Oops, sorry. Our cosine function, excuse me. That's our cosine function. Cosecant as the reciprocal of our sine function. And our tangent function as the reciprocal of our cotangent function. And these relationships gave us some tools we looked at in the beginning of this chapter to be able to manipulate expressions. Furthermore, we started to be able to look at the tangent function if we wanted to, if it was helpful, as the ratio between the sine function and the cosine function, as well as the cotangent function being its reciprocal. We could look at that as the cotangent function, as the cosine function over the sine function. And these built our reciprocal identities up here, our quotient identities there. We also spent quite a few sections on and had spent quite a bit of time with our Pythagorean identities. The idea that cosine squared theta plus sine squared theta is equal to 1, as well as its versions. We've got the 1 plus the tangent squared theta equaling secant squared theta, just by manipulating that primary Pythagorean identity, cotangent squared theta plus 1 equaling cosecant squared theta with a different manipulation, or any other manipulation of those that we want. So we have this kind of beginning list of things that we can do and ways we can manipulate our trigonometric functions. And essentially, we want to expand on that. You've seen with just this list on our sections on verifying identities, a little bit with our section on solving. You've seen some of the really interesting ways we can manipulate things with these tools. And I want to expand those tools and look at some of the other things that we can do. One of the big examples, because it's an important idea, is looking at what are we going to do when we have multiple angles that we want to have one of our functions apply to. So it would be nice to know what we could do with something like the cosine of a minus b. Now, you might think it would be nice to just say, hey, isn't that just the cosine of a minus the cosine of b? Unfortunately, that's not true. Just like the square root of a minus b isn't the square root of a minus the square root of b. But trying to figure out what this does become, it's actually a surprisingly interesting path to go down. Because if we learn just how to manipulate this one statement, there's a whole family of other manipulations that we get based on that. So what I'd like to do is build not only how do we manipulate the cosine of a minus b, but also look at how we build that family of manipulation tools that are born out of this one argument for cosine a minus b. Now, this is going to be a kind of a proof-heavy, construction-heavy video. I'm not going to be, giving you problems to work on. This is like, get a bowl of popcorn, sit back and watch these manipulations. But I didn't want to skip over all of these proofs. They can be a little bit, kind of daunting, a little, a lot to pay attention to after a while. So I am going to try to go at a fairly fast pace. But I want you to see them, because one of the main powers that we're going to gain by having these tools isn't just our ability to use the tools to do some of the little tricks you're going to get in your homeworks, but also just the ability to manipulate things and move things around and the flow of that movement. And I think looking at how all the constructions are made all at once, even though it's a lot, really helps give that sense of how fluid these tools are. So I'm just going to kind of jump into that and, take a deep breath and see how many of these we can go through. So it's going to be a lot of little tools, and I'll kind of stop every time we build what's considered a formal set of tools. I'll show you, hey, this is our formal set of tools. But the funnest thing for me is that all of these tools, this whole family of manipulation tools that we're going to build, all really come from one argument based on these two angles that you see up in this page, these two circles with the angles in them. The argument that we're going to make from these two diagrams are going to build the entire set of tools we're going to use. So let's look at this argument. So we're looking at this angle A minus B. If we're going to try to figure out what the cosine value or cosine ratio, if you prefer, for A minus B is, it might be nice for us to start with an angle A and an angle B. So I've got this green angle A and this blue angle B. Now I've put these angles A and B in particular locations to make the argument kind of visually more effective, but they could be in any quadrant, in any orientation, and this argument works just fine. You can imagine, hopefully, that if we take that kind of V made by the green and the blue angles, the A and B angles, and rotate it down, you get this angle, now in standard position, that is that difference between A and B. So, if we have a nice big angle A and the little angle B, this angle between them is the angle A minus B. And all I've done in this second diagram is rotated that angle down so it's in standard position. Now, what about these circles? We know our trig functions are defined based on circles. And, I could have made these circles any size and they would intersect both of those rays. So we're going to presume that we have made these circles of radius 1. So they are our unit circles. Again, if you wanted them to be a different radius, as long as the radii match, this argument still holds. It's just easier to have it be a radius of 1 to make these arguments. Okay, now the crux of the argument, the main thing that makes this work, is if we consider these two intersection points where the circle hits those rays and look at this length D. I'm going to call it D1. That length in this diagram is by necessity the same as this length on that diagram. I'm going to call that one D2. There are certainly different lines. They have different endpoints, but it's just the rotated version of that other line. So it shouldn't be a hard argument to make that those two distances have to be the same. Now what we're going to do with that is we're going to express that distance in terms of our trig functions to find a relationship between our trig functions for a minus b and our trig functions for a and b separately. Okay, how are we going to do that? Well, one of the reasons I wanted those circles on that radius of 1 is if we have those circles, we actually know the coordinates of all of these points. We know this point has a coordinate of the cosine of A and the sine of A by the definition of sine and cosine. Remember, the x value is associated with the cosine value, the sine is associated with the y value in standard position. Similarly, I don't quite like where that's drawing. Similarly, this point here, its x value has to be the cosine of b, and its y value has to be the sine of b, because of the definition of cosine and sine and the intersections with the unit circles. As long as those angles are in standard position, which they are. Now that's why we had to rotate our angle a minus b on this other diagram into standard position, because that allows this point to instead be the cosine of that new angle a minus b, and its y value be the sine of a minus b. And lastly, this little point down here, you might kind of be thinking, but there's no angle there. Well, that's actually nice because we know that angle is essentially at 0. So we know the coordinates of that point. It's at the point 1, 0. Now again, if for some reason you wanted to make that radius something else, you could. That would just be at the point r, 0, and your coordinates would be the cosine over r, the sine over r. Eventually all the r's would divide out. But it's an unnecessary part of the argument. We can, without loss of generality, let that radius be 1. Now, if we can, knowing that those two distances are the same, if we can write an expression for that distance in terms of this point cosine a minus b and sine a minus b, and the other distance in terms of the a's and b's separately, we'll have a relationship. And that's what we're looking for. Now, we do have to remember our distance formulas. So our distance formula, you may remember, I'm just going to write it in general here. Well, let me write it off to the side. So, yeah, remind you, distance in general is the square root of our x2 minus x1 squared plus y2 minus y1 squared. It's essentially just a version of Pythagorean theorem solved for the positive distance. So since we have our x and y coordinates, we're just going to use that to build our relationship. Now, it's a little bit of writing. I'll see if I can squish it all in, but we'll see what happens. So for this distance 1, our two x values are the cosine of b minus the cosine of a, quantity squared, plus the difference between our y's, sine of b minus the sine of a, quantity squared. So that's our distance 1. Our distance 2, same thing, but except we're over here. The difference between our x's, so the cosine of a minus b minus 1, because of that nice 1x value, squared, plus sine of a minus b, because again, that's our y value, minus 0 squared. So that 1, 0 is actually pretty handy. really, even right now, we have a relationship between, our cosine and sine of a minus b and our cosines and sines of a and b separately. So in some ways, we've gotten really close to the goal we want really fast. We just want, a simpler relationship. I'd really like to have cosine a minus b equals something. So I'd really kind of like to solve for that and simplify this. There's a lot going on. So how can we simplify this? Well, one of the great things is, the square roots look daunting, but because they both have square roots, we can really just kind of get rid of them. If the square root of all that is equal to the square root of the other thing, if two square roots are equal, the two things have to be equal. If we have the square root of a is equal to the square root of b, then a is equal to b. As long as everything's positive and all that, and since these are all squared, everything's positive. So there are conditions, for a and b in the proper conditions. They have to be positive. But the argument that those are the sum of squares and their distances have to be positive, we're totally safe. So the whole square roots can just disappear, which is nice. The bad part, if there is a bad part here, is that we have to FOIL these things out. I mean, you might take a look at that and go, oh gosh, I don't want to FOIL those out, but we really do have to. But maybe it'll be fun, and maybe something nice will happen when we do. So the square roots go away. Let's FOIL these things. Cosine of b minus cosine of a quantity squared turns into the cosine squared of b minus 2 times the cosine of b cosine of a plus the cosine squared of a. That's just our square of the first, twice the product, square of the last. Great. Plus this thing FOILed out. The sine squared b minus 2 sine b sine a plus sine squared a. Okay, great. That's that side FOILed out. That wasn't too bad. Now we got to FOIL out the other side. I even tried to give myself more space and I ran out of space, but that's okay. So we're going to FOIL out this other side. Again, the square roots have gone away, so we can just FOIL that. What do we get? We get cosine squared a minus b minus 2 times the cosine of a minus b times 1, but don't care, plus the 1 squared, it's just 1. So that wasn't so bad. And then, well, this one doesn't even have a constant on it, so that's just plus sine squared a minus b. Okay, so that wasn't too bad. So yeah, these two things are equal. Now it might look at first like we made kind of more of a mess of this as opposed to less, but if you remember our manipulation tools over here, that Pythagorean identity is about to come in super, super handy. We know that if we have the cosine of something plus the sine of that same thing, their sum has to equal 1. So if we look at what we've got here, if you notice this cosine squared b plus that sine squared b, those together make a 1. This cosine squared a and that sine squared a, those together make a 1. Okay, we're still left with minus 2 cosine b cosine a minus 2 sine b sine a. But that certainly got, I'm going to say, better. On this other side, this right-hand side, again, notice this cosine squared a minus b plus sine squared a minus b. The fact that it's a minus b doesn't matter as long as they match, and cosine squared plus sine squared gives us 1. Again, nice. plus that one. Nice. Minus 2 cosine A minus B. Okay, good. So that's quite a bit smaller, which is nice. Now we could start kind of adding some of these things together, but notice real fast, there's a 1 plus 1 on this side and a 1 plus 1 on that side. So we could turn those into 2, but we'd be subtracting them off anyway. They would just disappear. Also, if you allow me to do a couple steps at once, if we divide this side by -2 and that side by -2, the -2's cancel there and there, and we will be left with a surprisingly tight little statement. We will be left with the cosine B cosine A. Now, when we cancel those -2's, we're left with a plus sine B sine A is equal to, those ones went away with those ones. B's -2's canceled out, so it just equals the cosine of A minus B. And that was our goal. We wanted something that equaled the cosine of A minus B. So great, that's the big, the big long proof. Well, semi-proof, we'd have to technically prove that it doesn't matter the orientation. I made some assumptions in there, but even if you make a bunch of other ones, it still does work. We know that the cosine of A minus B is equal to this thing. I'm going to reorder that a bit just so it looks nice. But it's the cosine of A times the cosine of B plus, do notice it did change to a plus when we divided out that -2. The sine of A times, oops, the sine of B. Got a little squishy. Not happy with that being squishy. So it's not a small little formula, but it has the really great benefit of actually being true. So plus our sine of A, sine of B. So, okay, that's our angle difference formula for cosine. Well, that might seem like a lot of work for just one little tool, but remember, I said we're going to be able to build a whole bunch of other tools based on just this construction. Now, what did I mean by that? I want to show you what I meant by that. Let's say, for example, we now wanted to say, okay, that's great for cosine of A minus B, but what if we had the cosine of A plus B, and we wanted to manipulate that into something? Do we have to go through this whole argument again? Not at all. The cosine of A plus B is equal to the cosine of A minus the opposite B. Turn that addition into a subtraction, and hey, we have a subtraction tool. The tool we just built. It says that this is equal to the cosine of A times the cosine of the opposite of B plus the sine of A times the sine of the opposite of B. Oh, I put that extra parenthesis there. It wasn't hurting anybody, but don't forget my opposite of B. Okay, great. Except we can actually go a little further. If you remember, cosine is an even function. So the cosine of the opposite of B, the cosine of that negative B, is the same as the cosine of just plain positive B, because cosine's an even function. Similarly, the sine is an odd function. So if we turn that sine of B, or the opposite of B, into just sine B, that negative can come all the way out and turn this into a subtraction. So tightens up to a nice, fairly small argument. So again, this cosine of a plus b, we want to write it up here with this one. This cosine of a plus b is equal to a very similar looking object. The cosine of a cosine of b minus the sine of a sine of b. It is a little fun that when you're doing the angle difference for cosine, it becomes a plus, and the sum becomes a difference. That's an important thing to keep track of. So great, with just a little manipulation, we have not only cosine addition, but cosine subtraction. Well, that might be great for cosine, but what if we want sine functions? Do we have to go back to the big argument? And that's going to be our theme. No, not at all. If we want to know, say, the sine of a minus b, we don't have to go up to that big argument. We can just use our new tool. But wait, you might be thinking, our new tool is a cosine tool, right? But if you remember our cofunction identities, remember sine and cosine are really the same function, just shifted over. So our sine of a minus b is the same as the cosine of pi over 2 minus a minus b. So again, turned it into a subtraction. I want to use a little bit of manipulation there to turn this into the cosine of pi over 2 minus a plus b. Now you might have to spend a little bit while looking at that to convince yourself that that's true, but this negative is distributing to both of those, and then I'm grouping those first two. But then this is the cosine of a sum of this thing plus that thing. And we know how to handle the cosine of a sum. It's right there. That's equal to the cosine of pi over 2 minus a times the cosine of b minus, remember this is a minus, the sine of pi over 2 minus a times the sine of b. But by the same cofunction identity, these pi over 2's can again be switched. The cosine of pi over 2 minus a is the same as the sine of a, then multiplied by that cosine of b. You might have to go look up your cofunction identities, but it is a nice manipulation. And then our cofunction identity for the sine here means that this is equal to the cosine of a times the sine of a. So awesome, another new tool. The sine of a minus b is equal to the sine of a times the cosine of b minus the cosine of a times the sine of b. Notice for sine, the a minus b stays a subtraction. Cool. Okay, what about the sine of a plus b? Well, you can probably guess we would just have to do this manipulation again. And if you guessed that, it's a good guess. That's equal to the sine of a minus negative b, which again is the sine of a times the cosine of the opposite of b. We know that negative is just going to drop away because cosine, minus the cosine of a times the sine of the opposite of b. And again, we know that one's just going to come out. So equal to the sine of a cosine of b, again, because cosine's an even function. That negative is going to come out, make that a plus. The cosine of a sine of b. So great, another new tool. we're just ripping right along. Sine of A cosine of B plus cosine of A sine of B. Notice when sine is a plus, it stays plus. When sine is a subtraction, it stays subtraction. But in cosine, they flip. Well, great. That's our angle sum and difference formulas for both sine and cosine. Again, remember, this is all built from this one argument with our two lengths have to be equal, mixed with our ability to manipulate our trig functions. Those are very, very powerful tools that allow us to manipulate these things. What about tangent? Hopefully tangent isn't so bad. Actually, tangent is so not bad. I'm going to do both tangents at the same time. I want to look at A plus or minus B. I want to build a tool that's going to work if it's positive or if it's negative. If it's an addition or a subtraction. Because you've seen we can go back and forth pretty easy. So how are we going to do that? Well, we know, again, from our list of identities, that the tangent is equal to the sine of A plus or minus B over the cosine of, again, A plus or minus B. Well, gosh, we have tools for sine and cosine. So let's just use them. We know the sine of A plus or minus B, whether it's positive or negative, whether it's plus or minus, it's still the same pattern of sine, cosine, cosine, sine. So it'll be the sine of A cosine of B. And when this is positive, that'll be positive. When this is negative, that'll be negative. Cosine A sine B. So that's what's going to happen on top. Great. Divided by cosine of A cosine of B. And it'll be sine A sine B over here. But when this is a positive, that's going to be a negative. When the cosine is a subtraction, that's going to be an addition. So notice that. You'll sometimes see that plus or minus switch. You're like, why is that switched? It's switched for that association. With this plus or minus is the same as that plus or minus. But when this is a plus, like when this is a plus, the numerator is a plus, but the denominator is a minus. When this is a minus, the numerator is a minus, the denominator is a plus. So be careful about that. You'll often see that notation, and I wanted to make sure you got a talking through on it. Now, again, we could stop there and say, hey, that's the sum and difference formula for tangent. But if you think maybe we could simplify that a bit, like we did when we were verifying identities, you'd be absolutely correct. We can simplify it actually quite a bit. It's kind of fun how we do it. We're going to multiply the top and bottom of this by the cosine of A times the cosine of B, by 1 over, anyway, the cosine of A, cosine of B. That might seem like a weird thing to multiply the top and bottom by, but you'll see why it's nice. Okay, what happens? So when we distribute this thing to that first term, the cosines cancel. The cosines of B, anyway, cancel. The cosines of B cancel. And we're just left with sine of A over cosine of A. Well, gosh, what's that going to turn into? Plus or minus. In this term, the cosines of A cancel. And we're just left with the sine of B over the cosine of B. Well, again, gosh, you know what that's going to turn into? The sine of B over the cosine of B. All over in the denominator. Cosine A, cosine B multiplied by 1 over cosine A, cosine B. Everything cancels, left with a 1. minus plus. Got to be careful about that. Sine A sine B over cosine A cosine B. All right. Sine A sine B over cosine A cosine B. Okay, we don't have to separate those, but you can see that's going to turn into tangents. So great. All those become tangents. So the tangent of A plus or minus the tangent of B all over 1 minus plus the tangent of A times the tangent of B. Again, just this flow of how we can manipulate these. I mean, no one's going to ask you to memorize all of this. Not even me. So yeah, don't memorize all of this. But I wanted you guys to see this flow of all these tools and how they kind of manipulate one into the other. So our tangent of A plus B, you can write these combined too, like I did down here. So the tangent of A plus or minus the tangent of B over 1 minus plus. If you do, you just have to remember that this plus or minus becomes a minus plus on that side. Tangent of A, tangent of B. So great, that's our sum and difference formulas for sine, cosine, and tangent. What if you had one for secant? Well, we don't build one for secant. If you have something in secant, take its reciprocal, turn it into a cosine, use the cosine tool, and then simplify it from there. So, great. That's our angle sum and difference formulas, all built again from this argument. Now, if you thought we were done, it's been about 20 minutes or so. Be nice to be done, but there are more tools we can build. Again, without making a new argument. We have some what are called double angle formulas. So if we have the sine of 2 times A, what happens when we double an angle? Now, does that turn into twice the sine of A? It doesn't. That's unfortunate. Yeah, but then what it actually becomes gives us actually a cool manipulation tool. But how are we going to build, how are we going to figure out what sine of 2A is supposed to turn into? Well, we already did. We already built the tool. The sine of 2A is the sine of A plus A. That's what 2A means, right? Well, okay. We know what the sine of A plus A is. That's the sine of A times the cosine of A plus the sine of A times the cosine of the other A from the formula we just built. And hey, those match, so we can add them together. 2 sine A times cosine A. Great, that's our double angle formula for sine. We could frankly add it up here. Sine of 2A equals 2 sine A cosine A. This is a super good formula to know, by the way. If you're going to memorize only one trig function in your life, memorize this one. It's so super handy. But double angle formula. It's just a modified version of our angle sum formulas. Could we do that for, say, tangent? Well, of course we could do that for tangent. You're going to get tired of me asking you if we can do things. Of course we can do things, as long as we learn how to manipulate these. So let's say tangent of 2A. If we look back up at that formula, that means the tangent of, well, let's write the A plus A first, because that's our link to our angle sum formula. But that means we have the tangent of A plus, because the numerator keeps the sign, the tangent of A over 1 plus, Well, in the denominator, the sign changes, right? So 1 minus the tangent of A times the tangent of A. So it simplifies a little bit into 2 times the tangent of A over 1 minus the tangent squared of A. Okay, great. We can add that to our formulas. Tangent of 2A. I know I'm going through these kind of fast. I told you I was going to go through them kind of fast. You can always stop, slow things down, go back. But again, my goal here is to give you a sense of how all of these manipulations are possible and where all of these tools come from. We'll work together on what we can do with them. But I want you to see them all grow and kind of birth from that same argument, because this is all coming from the fact that those two lines are the same length. So let's well, we did sine and tangent. We're kind of waiting to do cosine here. So let's do that. Cosine of 2A. Again, that's the cosine of A plus A. So according to our formula, that's the cosine of A, cosine of the other A, minus, again, remember cosine, the addition, subtraction switches, the sine of A times the sine of the other A. But come on, now we got cosine times cosine, sine times sine. This turns into cosine squared A minus sine squared A. It almost looks like the Pythagorean identity, but not quite. It's a subtraction instead of an addition. Be careful about that. So great, the cosine of 2A is equal to the cosine squared of A minus the sine squared of A. We could stop there. But the fact that we have the Pythagorean identities, we could manipulate this if we wanted to. That cosine squared of A, we know that's equal to 1 minus the sine squared of A, based on the Pythagorean identity. And that might be handy, because then it would meld with the other sine squared. We'd end up with 1 minus 2 sine squared A. So we could have that as our double angle formula for cosine if we wanted to. Or instead leave the cosine squared A and turn that sine squared into 1 minus cosine squared A, again using the Pythagorean identity. We'd do some distribution, we'd get cosine squared A plus the other cosine squared A. So we'd have 2 cosine squared A minus 1. So we could have that. Any of these three are very nice simplified combinations for the double angle formula for cosine. And actually, they're all so handy that we tend to keep all three of them around. This is one of the advantages of the double angle formula for cosine, is it's very flexible because it's got that square in it, and the Pythagorean identity allows it to be so nicely manipulated. So when you see this in your tools, notice that the cosine double angle formula, you've got some options. Sometimes it'll be like, well, which one of those am I supposed to use? Well, it depends on what you're doing. Which one do you want to use? If you have cosine 2A, but all you know is things about sine, well, using the version that only has sine in it can be handy. So it is a nice manipulation tool. So great, we got some double angle formulas. Well, what if you had, say, do we have a triple angle formula? We don't. We could make one. That's equal to the sine of 2A plus A. We know what the sine of 2A is. We know how to handle a plus. So we could build a sine of 2A or 4A or 5A or 6A or anything we wanted to. So, we don't need new formulas for those. We could build them if we wanted to, or we could just manipulate our particular problem using these tools if we need to. Let's see, what else might be handy that you'll use a lot? Well, the fact that this double angle formula for cosine turns into a couple of different things really is surprisingly handy. The fact that this cosine of 2a is equal to, I'm going to use this one, the 1 minus 2 sine squared a. This is a handy fact, a handy relationship, because we can solve this for the sine squared of a. So let's take that and go cosine of 2a and subtract the 1, get negative 2 sine squared a, and then divide off that negative 2. I'm going to change the order while I do this. That's going to be the sine squared of a is equal to, I'm going to actually do a lot of manipulation here, put that negative up there, switches our subtraction, so 1 minus the cosine of 2a over 2. So look for, spend a little while looking at that, make sure you're happy with all those signs. But this is actually a really useful formula. We won't use it in this class in trigonometry, but you'll use it in calculus and physics a tremendous amount. It's called the power reduction formula. If you have a squared function, we can use this formula to get a non-squared function. Okay, you have to put in that too, but sometimes the square is a pain. It's a very handy tool. We could also take a square root here. Take square root of both sides, and that sine of a is equal to plus or minus. We'll talk about how to be careful with that plus or minus. 1 minus cosine of 2a over 2. Okay, why is that handy? Well, if we called, say, 2a, say, theta, then a would be equal to half of theta. That's certainly true, right? So instead of calling this cosine of 2a, if I call that cosine of theta over 2's square root, sorry, my handwriting gets messy down here, then this a would turn into the sine of theta over 2, and we'd have our half angle formula. Shouldn't be a surprise that our double angle formula solves into our half angle formula. So awesome, half angle formula. Can I add that to the list up there? I'll do it in a second. If we instead grabbed this version, remember this was our cosine 2a equals 2 cosine squared a minus 1. That was our other, one of our other versions of a double angle formula for cosine. If we solve this for cosine a, we'll get another half angle formula. So again, we're going to add the 1 plus cosine 2a, and divide the 2. So get a nice cosine squared a equals 1 plus cosine 2a over 2. Again, this, just like this one, these formulas are very handy later. It's our power reduction formulas. Notice they're almost the same. One's a plus, one's a minus. Really cool thing about deriving things from this double angle formula for cosine. So we could stop there. Again, we won't use that tool much in here in trig, but in calculus and physics, you use those power reduction formulas a lot. But we could continue to solve. And again, I'm going to switch sides here just for my own comfort. Our cosine of a is then equal to plus or minus. And again, we'll talk about what we have to do with the plus or minus when we talk about using these tools. 1 plus the cosine of 2a over 2. Do that same substitution just to be able to express this as a half angle formula. Now, why might we do this? Again, we'll talk about why these tools are helpful and what we're going to do with them. But right now, I really just kind of want to focus on I hate to say it, but the beauty of these tools and how we could move these things around and have them all flow. So it's really interesting, I think, that these two tools are so close to each other. Lastly, I will stop after this one. If we went to tangent of a half angle, you can probably imagine from the work we've done before, this is just sine of half an angle over the cosine of half an angle. We know what the sine of half of an angle is. It's the square root of, what was it, 1 minus the cosine of 2a over 2 over the square root of 1 minus the cosine of 2a over 2, except this one was plus. Remember, the cosine of 1 has the addition. And you can imagine we could cancel out the 2's and deal with the square roots, simplify this to one big square root, 1 minus cosine 2a over 1 plus cosine 2a. So we could stop there if we wanted to. Actually, there are some really cool things you can do to even simplify this. And do a little bit tighter of an argument. They're actually quite nice. But we've got these half angle formulas to go along with our double angle formulas and our sum and difference formulas. And there are some other identities. Our sum to product identities are built in a very similar type of way. So all of these tools, these 3 tools down here, our double angle formula, technically our 6 angle sum and difference formulas, these add to our list of identities based on this argument and a skill of being able to manipulate these. Now, hopefully this wasn't too horrifyingly overwhelming, but I want to remind you that no one's going to ask you to go through and do all of these derivations. No one's going to ask you to have these memorized. I do recommend you memorizing this one for this double angle formula for sine, for particularly any of you going on to calculus or physics. It'll make your life just 100% easier. And the Pythagorean identity, we expect you guys to know. The reciprocal identities and the quotient identities, we expect you guys to know. But all the little details in here, we want to make sure you get familiar enough with them that you can kind of see a problem or see something happening and go, wait a minute, I think there's a tool I could use, and go to your list of identities and go, yeah, there's that tool, and bring it. So we'll talk as we meet about how we use these tools and how we can kind of adapt these tools for different situations. But I really did want you to see where they come from and how they're built and where they how they all come out of the same argument and flow together. So read through those sections, play with them, let me know what more I can do to help. And gosh, I'll talk to you guys real soon. Have a wonderful day.